Bismillahirrahmanirrahim. I welcome all the engineering students, especially the students of Khaja Farid University of Engineering Information Technology. This is lecture number 20 of Engineering Dynamics. Dear students, we have discussed the basic principle of work energy principle and solving the problems with the, having velocity and acceleration, considering the kinetics, but using the energy method. That work done, basically moving the body from point 1 to 2 is the kinetic energy, and of course the change in kinetic energy is equal to the work done. This is a basic principle of the work energy principle, I think the kinetic energy and the work. So let's talk of the unsolved problems by using the energy method. This is the problem number 3-97. The spring is stretched when x is equal to 0. If the body moves from the initial position x1 is equal to 100 mm to the position x2 or 200 mm, determine the work done by the spring on the body and determine the work done by the body by its weight. So we have to find the change in potential energy converted into work done, and of course the change in the elastic potential energy to convert it into work done, and is moving from x1 is 100 to 200 millimeters. So we have to find the work done by moving the body from this point to this point. The mass is 7 kilogram. Of course the stiffness is 4 kN per meter and is moving on a incline of 20 degree. So dear students, x1 is 200 millimeter, x2 is x1 is 100 millimeter, x2 is 200 millimeter. So there is a movement of about 100 millimeter. We need to find the work done for the case of change in elastic potential energy due to weight. So for the first case, of course, the change in kinetic energy is half k x1 square minus x2 square. We have discussed already. There is 1 by 4 exponent 3 is the value of k stiffness, and x1 and x2 converted into meters, 0.2 and 0.1. We get a work done, of course, that is the spring on this, that is minus 60 joules. Similarly, the height, that is mg h2 minus h1, mg 0.2 to 0.1 is, and then there is a sine of 20 degree, of course, the decrease from here to here. So this is the vertical direction, and of course the height at 20 at initial position, and then when you move from means at x is equal to 100, and then move downward to further 100 millimeter, that's 200. We can find the another potential energy, that is, and of course we take the vertical component, that is sine of 20, and that is the work done by the weight. Work done by the weight, which is 2.348. It is moving downward. Of course, it is in the positive. It should be joule. Please take it. It is not newtons, joules. Thank you. Next, move to the problem 3-101. In the design of a spring bumper for a 3,500 pound car, it is desired to bring the car to stop from a speed of 5 miles per hour in a distance equal to 6 inches of spring deformation. Specify the required stiffness K for each of the two springs behind the bumper. The spring are undeformed at the start of the impact. So initially the springs are undeformed, right? When the strike, of course, by 6 inches movement, the car is moving at 5 miles per hour, it should stop. We need the value of the stiffness of the spring to be used with this particular spring bumper system. So it is just the change in kinetic energy is converted into work done. So the work done, of course, is basically the elastic potential energy is half kx square multiplied by 2, because there are two springs. So it is change initial energy is 0, the final energy half mv square. From here we know the value of k and the mass, and of course the x, which is 6 inches. So I put the value here. So it's mv square upon 2x square. This is the mass. Right, 3,500 pound. Sorry, it's 3,500 pound. Yes. So I divide by 32.2. This 2 is this one. Now this is miles. 5 by 30 into 4 whole square over 6 by 12 whole square. That is velocity. Velocity is converted into, I convert feet per second, and this one converted into feet whole square. There's a 974 pound per inch stiffness of the spring is required. Next problem is 3-106. The man and his bicycle together weighs 200 pounds. What power P is the man developing in riding up a 5% grade 5% grade at a constant speed of 5 miles per hour. Sorry, 15 miles per hour. It is moving with 15 miles per hour, and the weight of total the cycle and the person is 200 pounds. I need to find what power is developing is. So power is basically work done multiplied with the velocity is y dot, where here in this case y dot, of course there is a very small incline. There's 5, the slope is given 5, and this is 100. So we will take the y dot, it is v, of course, sine of theta, velocity in the vertical direction, moving vertical direction, v is sine of theta. So it is 5 by 100 here. So theta is equal to 10 inverse, 5 by 100 is 0.01, we get 2.86, and sine of theta is 0.0499, or you can do directly 5 by 100. You can find the sine component, which is just take this one 5 square 100 square under root, and then take the hypotenuse, and you can take 5 over this. You can get the slope. So with the slope I find the angle and find the sine theta. So that is the power. Power is the power, the force times velocity. Velocity is v sine of theta. If it is moving with straight line, of course the velocity v will be taken, but there is slight slope of 5 by 100. I therefore find the value of theta. So power is equal to, is the weight, right? And then there is a velocity. Velocity is 15 miles per hour. So 15 into 44, it becomes feet per 30. That becomes meters per second, and then it's 0.04. That 99 sine of theta. It is 219.7 feet pound per second. To convert into horsepower, so 1 foot pound per second. So 350 feet pound per second is basically 1 horsepower. I just divide with 350, I get 0.4 horsepower is being developed by the cycle rider to moving this cycle on a small incline angle of 2.86 degree. Next problem 3-109, the 2 kilogram collar, this collar is released from rest at point A and slides down the inclined fixed rod in the vertical plane. The coefficient of kinetic friction is 0.4. Calculate the velocity v of the collar as it strike the spring, and v the maximum deflection x of the spring. So once you move from this point to this point, this is basically a change in gravitational potential energy. The only thing which is basically reducing is energy, that is coefficient of friction, which is of course mu k times n multiplied by 0.5. So first of all, and of course change in kinetic energy is basically work done. So summation of Fy is equal to 0. If you see free body, make the free body diagram, and at any point, this is a normal reaction, weight is in downward direction, right, and frictional force is a force in the upward direction. So that is my normal reaction, right, and this is my W, this is W cos theta, and that is my normal reaction, and this is the direction in which it is moving. I say taking this one is x and this one is y, so therefore it is like this. So W cos theta, and why I did make this, because there is no direction in movement in the y direction. So the summation of y is equal to 0 to find the value of n, because from the normal reaction I can find the frictional force. So changing kinetic energy is equal to the work done. So in this case the work done is 2 into 9.8, 0.5 sine of 60. So how we can get this? Of course 2 kilogram mass, and this is the height. So m g h is basically 0.5 times sine of 60, right, minus the frictional force, which is 0.4 times 9.8, right, this is my frictional force, and distance traveled on this slide is 0.5 meter, so this should be subtracted. This is the work done, which is converted into velocities, half mv square. M is the mass of 2 kg. Here the only unknown is velocity. This velocity is with the slider which can strike the spring with velocity of 2.56 meter per second. Next is the change in kinetic energy. We have to find what is the maximum deflection on the spring. Dear student, again the change in kinetic energy is equal to the work done. In the same way, it's 2 into 9.81. Now it has the some deflection of the spring in this direction. So total height becomes 0.5 plus x sine of 60. So this is sine of 60 minus 0.4 9.81, similarly 0.5 plus x. Here the equation becomes in the quadratic equation. I solve it to take the positive value. It is 0.0989 meters or 98.9 millimeters, or you can say it's about 9.9 or 10 centimeters is the deflection of this spring. This is problem 3-111. The problem 120 pound woman jogs up the flight of stairs in 5 seconds. Determine her average power output. Convert all given information to SI units and repeat your calculations. So 9 feet height, and the woman is moving to the height of 9 feet. Of course, it is basically the force time velocity. It is converting into 5 seconds. I can find out the power. So power is equal to WH, work done per unit time. So power is equal to 120 is the pound mass, and distance traveled is 90, and work done is done in 5 seconds. To convert it to horsepower, I divide into 550, and of course this 0.393 horsepower. Now to convert into SI units, of course the height is 9 feet, so I converted 9 feet into meters, 0.3048 or 2.74 meters. So it is W is equal to, it is 120, sorry, this is 120 pounds. So it is 120 pounds. 120 pounds converted into newtons. 1 pound is equal to 4.448 newtons from the previous knowledge. So I multiply to get 534 newtons. So I have force in newtons and a height in meters. I just put WH by delta T, and I get WH delta T is 293 watts. Thank you. So this is the into 293 watts, or if you want to convert this one also in horsepower, so you can just divide with 746, you will get the same answer. Let's go to the problem 3-129. The ball is released from position A with a velocity of 3 meters per second and swings in a vertical plane at the bottom position. The cord strikes the fixed bar at B, and the ball continues to swing in the dash arc. This arc in this way. It is basically swing in this way, right? So arc. Calculate the velocity VC of the ball as it passes position C. When it passes position C, what is the velocity? Basically, there is a cord with which a bob is attached, which is moving with 300 meters per second, and then it swings like this, you see, and we need to find the velocity at point C when its height is 0.6 meter. This angle of from where we release the ball is at 60 degree, just like a simple pendulum. Okay, so let's see of course the change in kinetic energy is the work done. As far as the work done is concerned, we are here at this height, right? That is mg into 1.2 sine of 60. So it is mg. The change in kinetic energy, of course, sorry, because the work we are talking of the work done. So here the work done is simple. It's mg times 0.8 minus 1.2 cos of 60, 1.2 cos 1.2, and that is a cos of 60, of course. Why I take cos of 60? I take this one height, so this is cos of 60 height. So initial final height is 0.8, and initial height was 1.2 cos of 60. The final one is work done. Distance traveled is equal to half mvc square. The velocity at C is unknown. The velocity at A is of course 3 meters per second square. So we just put the value. Mass pass cancel out value of G, and this difference is of course becomes 0.2 half, and the only unknown is VC with 12.92 meters square per second square, or 3.59 meters per second. So dear students, just the change in potential energy is the work done, of course, is converted into kinetic energy. This is the work done by the gravitational force. It moving from this height 1.2 cos of 60 to 0.8. That's converted into the change in kinetic energy. I just use the kinetic energy and work done principle. The change in kinetic energy is basically work done. Let's move to the next problem 3-131. Once underway at a steady speed, the 1000 kilogram elevator A rises at the rate of 1 story, 3 meters per second. Determine the power input P in into the motor unit M, this motor, how much power is required if combined mechanical and electrical efficiency of the system is 0.8. So problem is not difficult. We just make the free body diagram. Of course, the weight is in the downward direction 109.81. These are the 4 tensions, right? And it moved from this point to this point, that is to the height of a single story of 3 meter, right? This is SA. So summation of y is equal to 0, downward movement. So take, because if they say it is moving downward, so it is 9810 minus 40, this is 40, is equal to tension in the cable is one cable is 2490 newtons. So the length of the cable is of course 4 SA, because this is moving, plus the constants. We just take the, because the length of the rope is changing, so L dot is equal to 4 VA. 4 VA is minus 3. Why are we taking minus 3? Because moving in the opposite direction, because we're taking y downward is positive, so it is minus 12 meters per second. Power is equal to minus t times L dot, velocity. So t is minus 2450, the opposite force, because there is a force applied by this, is the opposite force is minus t. So multiply by the velocity, you get 29400 watts at 29.4 kilowatts. Now this is the power developed by this. What is the input power? This is power output required. What is the input power? As efficiency is P out by P in. So this should be equal to P in is equal to P out by E. And we just get P in is equal to 29.4 divided by 8. 36.8 kilowatt power is to be given by the motor, such that it delivers a power of 29.4 kilowatt, which is being required. Let's move to the problem 3-135. The 6 kilogram cylinder is released from rest in the position shown and falls on the spring, which has been initially recompressed 50 millimeter by the light strap and the restraining wires of the spring. So initially it is slightly depressed by some distance, that is maybe 50 millimeters given. If the stiffness of the spring is 4 kN per meter, compute the additional deflection delta of the spring produced by falling the cylinder before it's rebound. This strip basically, it compressed the spring by 50 millimeter. Now this 6 kilogram block, when strike on this plate, of course the spring will further deflect. We need to find this deflection when it, of course, 6 kilogram weight strikes on the spring by a height of 100 millimeter. So again, the change in potential energy is converted into the, of course, the work done, or you can say work done is in kinetic energy. So change in kinetic energy is equal to Q is equal to 1 by 2 is equal to delta T is equal to 0. Why it is 0? Why it is 0? Because when it falls on this, then everything goes to 0. Because when it falls, spring will compress and then becomes to the rest, and there is no motion. So the work done is 6 into 9.81, right? 6 into 9.81, and distance is of course 100 plus delta. So it is 0.1 plus delta. This is the work done. I just subtract minus delta T, the change in kinetic energy. So it is 4,000. So it is 4,000 kx square. So students, we have so this is the weight force, and then of course balanced by the spring force. It is 4,000 x into dx. Moving from 0.05 the initial displacement to the 0.05 plus delta is final displacement, that is equal to 0. If you simplify, we get a relationship in delta square. We get the value of delta is 0.024 meter or 24 millimeter. So when you solve the quadratic equation, you take the positive value of delta and you get this. So the change in kinetic energy, that is because the work done because of the potential energy is a change in kinetic energy, or that is because of the work done because of elastic forces, right? Because there is no movement, there is no kinetic energy. The work done is basically is equal to delta T, or delta T, there is no change in kinetic energy, so therefore it is 0. So work done is, this is because of the work done due to the gravitation was positive, and this is the work done by the spring forces, elastic spring force in the positive direction is 0. Here the change in kinetic energy is 0. So therefore it is work done is equal to delta T, which is equal to 0. In other words, you can say the net work done is on the body is 0 by the gravitational forces and the elastic forces. Next, move to the problem 3-136. Extensive testing of an experimental 2,000 pound automobile reveals the aerodynamic drag force Fd and the total non-aerodynamic rolling resistance force Fr is to be shown in the plot. Determine A, the power required for steady speed of 30 and 60 miles per hour on a level road. B, the power required for a steady speed of 60 miles per hour both up and down a 6% incline, and the steady speed at which no power is required going down is 6% incline. This is the basically a relationship given to you, and this is force and this is the speed, and the drag force is this one, right? And this rolling force, this one is constant. The drag force is a parabolic. This becomes, of course, the drag force is equal to kV square. From here, you by taking any one of the value, you can find the value of the constant k, and you get the relationship for the drag force, and you also find this rolling force. Rolling force is constant. So if you make the free body diagram, so this is my car, right? So the downward force is a drag force and the rolling force, and the weight is downward is W sin theta, W cos theta, and this is the Fp. This is the Fp. What we need to find actually, the power required. This is the force P which is moving upward. We need to find power. So theta is equal to 6% means 6 by 100 is 3.43 degree. The drag force is kV square from the graph. From the graph, if I take when drag force is 50, when drag force is 50, I get this one is speed is 60 miles per hour. I get the value of k, which is basically 0.01389 pound r square per mile square, or Fd is equal to 0.01389 v square. Now summation of Fx is equal to 0, this and this. So it is basically Fp minus Fr minus Fd minus mg sin theta is equal to 0. So Fp is equal to Fr plus Fd plus mg sin theta. This is my equation number 1. Now the first question in the level road, when theta is equal to 0 and the velocity is 30 miles per hour, the drag force I just the k v square 12.5. Put this value in equation number 1, right? The rolling force is constant, which is here. You see, this is 50. So it is 50 plus 12.5 is 62.5 pound, right? Is 62.5 pound, because this mg sin theta goes to 0. The sin theta becomes 0. When theta is 0, sin theta is 0. So Fp is simple Fr plus Fd. Fd is this much, and then when moving on the level road, that is only 62.5 pound. Now, when velocity is 30 miles per hour, power is equal to Fv, is 62.5, and the velocity 30, and this 5280 or 3600 I convert into feet per second, 550 divided to find the in horsepower. When moving 60 miles per hour, of course, drag force is same. The only thing which is to be changed is, of course, rolling force remains same. Only thing changes that the drag force, it becomes 100 pound by using the same F is equal to kV square. And then at 60, of course, Fv, this is force, which is 100, and this 60 into 5280 divided by 3600 convert this one into, of course, feet per second, divided by 550 to convert into horsepower. 16 horsepower is being developed at a 60 miles per hour. Now the next question is, when theta is moving up the hill at a 6% incline, which angle is 3.43, so F is equal to 550 plus 200 sin 3.43 is equal to 220. Same equation, this equation. I put the value of mg sin theta. But this component of the weight is also be included, and the more power is required. It is 35.2 pound for P up. For P up, and then we talk of this is not pound. Sorry, this is 35.2. I'm sorry, this is 35.2 horsepower. So you see, in this case, more power is required as in the case of previous case. Now similarly for down, so Fd is equal to 550 and minus 2003.43, of course, weight in the downward direction. It is minus 19.78 pound, and P down is equal to minus 19.78, and then I multiply with the velocity and 550, we get only minus 3.17 horsepower. So this is the braking power, basically negative power required to move to slow down. Now the last part of this question, the steady speed at which no power is requiring down the steady speed. Steady speed means velocity is constant. So Fx is equal to 0 in that case. 50 plus kV square minus 2003.43. I just find the velocity, which is 70.9 miles per hour with steady speed. So steady speed means there is no acceleration So that is equal to 0. 50 is the rolling force, this is the track force, this is the weight component downward. The same equation, but only thing is that should be equal to 0. So I just put this one and find the value of the velocity. Thank you, students. I solved some of number of problems, 6-7 problems with variety of problems regarding the work and kinetic energy principle, and this topic is completed. My next lecture will be soon, maybe tomorrow. That lecture is regarding the work energy complete principle, in which of course the kinetic energy, potential energy, and then the potential energy because of the gravitational potential energy and the elastic potential energy. So we can say the V1 plus T1 plus work done is equal to T2 plus V2. The change in energy is equal to the work done. Now we include both kinetic energy and the potential energy. Thank you very much.